Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. Also, there is an overhanging span CD. In the span AB, there is a point load 72 kN acting in the center. In the span BC, there is a uniformly distributed load 24 kN per meter acting for the full span. In the overhanging span CD, there is a point load 15 kN acting in the point D. In the point A, there is a fixed support. In the point B and in the point C, there are hinged supports. Span AB is 4 meter long, span BC is 5 meter long, the overhanging span CD is 2 meter long. In this beam, totally we have to find 5 moments. In the fixed support, there will be a moment. Here the moment is MAB. In the joints, there will be 2 moments. In the joint B, there are 2 moments MBA and MBC. In the joint C also, there are 2 moments MCB and MCD. So, totally we have to find 5 moments. Also, we have to find 3 reactions RA, RB and RC. In the joint C, we can easily calculate the moments because on the right of C there is overhanging. To calculate MCD, we have to find the moment in the point C from the point D. In the overhanging span CD, there is a point load 15 kN. The distance of overhanging is 2 meter. When we multiply the load 15 with the distance 2, we will get MCD, which is equal to minus 30 kN meter. Since MCD is acting in the anticlockwise direction, we have to apply the load with the negative sign. So we have got a negative moment. The values of MCB and MCD will be same, but only the direction will be different. MCD is acting in the anticlockwise direction, so it will be negative. MCB is acting in the clockwise direction, so it should be positive. But the values of MCB and MCD will be same. In this concept, we can calculate MCB. MCB is equal to 30 kN meter. So it is the easiest way to calculate MCB. We have to just change the sign of MCD. So we will get a positive moment. Now let us calculate the fixed end moments. No need to calculate the fixed end moments in the overhanging span CD. Only calculate the fixed end moments in the span AB and in the span BC. First, let us calculate the fixed end moments in the span AB. For that, we have to assume the span AB is a separate fixed beam. In the span AB, there is a point load 72 kN. It is acting on the center. The formula to calculate the fixed end moments are minus WL upon 8 and positive WL upon 8. M of AB is negative because it is acting in the anticlockwise direction. M of BA is positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 72, L is 4. When we apply the values, we are getting M of AB and M of BA. Now, let us calculate the fixed end moments in the span BC. In the span BC, there is UDL 24 kN per meter. It is acting for the full span. The formulas to calculate the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Here W is 24, L is 5. When we apply the values inside the formulas, we are getting M of BC and M of CB. In the stiffness matrix method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. And in the roller support also, there will be slope. In this beam, there are two hinged supports. In the point B and in the point C, there are hinged supports. So, the number of supports where slope occurs is 2. In the point B, there is theta B, and in the point C, there is theta C. So, in this analysis, there are two unknowns. If we calculate these two unknowns, we can easily find the final moments. Now, let us make the fully restrained structure. In the fully restrained structure, there will be no displacement. We know that only in the fixed support there will be no slope. So let us remove the hinged supports from the point B and from the point C and replace them with the fixed supports. In the restrained structure, no need to consider the overhanging span. Now in this beam there will be no displacement because all of the supports are fixed. That is why it is called the fully restrained structure. We have made the fully restrained structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. The coordinates are in the points B and C. Because in these points only, we have the unknown displacement, that is slope. The coordinates should be made in the clockwise direction. You can see that both of the coordinates are in the clockwise direction. Now let us see the formula to calculate the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix. PL matrix is the moments developed in the coordinates due to the given load. P matrix is the final forces acting in the coordinate direction. K matrix is the stiffness matrix. Inside the delta matrix, P matrix and PL matrix, we will have two values. Because in this analysis there are two coordinates. Inside the delta matrix, we will have the slope values theta B and theta C. In this formula, first let us calculate the PL matrix. We know that inside the PL matrix, we will have the moments developed in the coordinates due to the given load. In this analysis, there are two coordinates. In the point B and the point C, we are having the coordinates. In the point B, we have calculated two fixed end moments, M of BA and M of BC. We have to add them. After adding, we are getting minus 14. In the point C, we have calculated a fixed end moment, that is M of CB. Let us apply that. In this formula, now let us calculate the P matrix. P matrix is the final forces or moments acting in the coordinate direction. Inside the P matrix, we have to apply the values very carefully. The first value from the first coordinate, the second value from the second coordinate. Using the overhanging span CD, We have calculated two final moments in the point C. Now let us check the first coordinate. In the first coordinate B, there is no moment developed due to the overhanging span. So in the first coordinate, it will be 0. Now let us see in the second coordinate. In the second coordinate, we have calculated two moments, MCB and MCD. Here we will have some confusion which moment we have to select. MCD is acting in the overhanging span, so we should not select it. MCB is acting in the span BC, so we have to select MCB. MCB is 30. Let us apply the value. In this formula, we have calculated PL matrix and P matrix. Now let us calculate the stiffness matrix. Let us see how to calculate stiffness values inside the stiffness matrix. For that, first we have to apply the unit displacement in every coordinate. In this analysis, we are having two coordinates. In the point B and in the point C, there are coordinates. So, in these coordinates, we have to apply the unit displacement. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. We have to be very careful. We have to apply the unit displacement in the fully restrained structure and not in the given beam. Now let us see the size of the stiffness matrix. For 3 coordinates, the size will be 3 cross 3. For 2 coordinates, the size will be 2 cross 2. For 1 coordinate, the size will be 1 cross 1. In this analysis, there are 2 coordinates, so the size will be 2 cross 2. Inside the matrix, there will be 2 rows and 2 columns. In this matrix, first let us calculate the first row. For that, we have to apply unit displacement in the first coordinate. Let us apply unit displacement in the point B. In the point B, there is a fixed support, but when we apply unit displacement, it is no longer a fixed support, it becomes a hinged support. Because in the fixed support, there will be no displacement. Since we apply unit displacement, this fixed support becomes the hinged support. Now let us see how to draw this curve. We are applying unit displacement in the point B. The point B is a joint. It is connecting two spans. So we have to make two clockwise curves, one curve towards the point A and one curve towards the point C. Both of these curves should be made in the clockwise direction. Now we have to see the direction of the arrows. This arrow indicates upwards, so the curve comes above the span. This arrow indicates downwards, so the curve comes below the span. We have to give some gap between the fixed supports and the curve. You can see that I have given some gap between the fixed supports and the curve because in the fixed supports there will be no slope. Same like this, the coordinates should be made in the clockwise direction. Now let us calculate the stiffness values. The stiffness values should be calculated in the order. First from the first coordinate, then from the second coordinate. In the first coordinate we have K11. Let us calculate that. To calculate K11 from the joint B, we have to look on both the sides. On the left side there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of BA is 4 meter. Let us apply that. Now let us look on the right of B. On the right of B also we are having fixed support. So we have to apply the same formula 4EI upon L. Length of BC is 5 meter. Let us apply that. For K11 we have two stiffness values. Let us add both of them. After adding we are getting 1.8 EI. Now let us calculate K12. For that, from the point C we have to look on both the sides. On the right side there is nothing. On the left side there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of CB is 5. Let us apply that. Finally, for K12, we are getting 0.4 EI. We have calculated the first row. Now, let us calculate the second row in the stiffness matrix. For that, we have to apply unit displacement in the second coordinate. In the point C, there is a fixed support, but when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. Now let us see how to draw this curve. We are applying unit displacement in the point C. So from the point C, we have to make a clockwise curve towards the point B. Then we have to see the direction of the arrow. This arrow indicates upwards. So the curve comes above the span. We already know in the fixed support there will be no slope. So we have to give some gap between the curve and the fixed support. You can see that I have given some gap. That is why the slope curve ends before the point B and it cannot continue after the point B. Now let us calculate the stiffness values. We know that the stiffness values should be calculated in the order, first from the first coordinate, then from the second coordinate. In the first coordinate we have K21. Let us calculate that. For that, from the point B, we have to look on both the sides. On the left side, there is no slope curve. If there is no slope curve, there will be no stiffness value. Now, let us look on the right side. On the right side, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of BC is 5. Let us apply that. Finally, for K21, we are getting 0.4 EI. Now, let us calculate K22. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of CB is 5. Let us apply that. Finally, for K22, we are getting 0.8 EI. In the stiffness matrix, we have calculated both of the rows. Let us apply the values. EI is constant. Let us keep it outside. In the system displacement formula, we have calculated everything. Let us apply the values. EI inverse is 1 upon EI. Then let us add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to calculate inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and found the inverse. Then we have to multiply these two matrices. After multiplying, we are getting the final answers. In this analysis, the system displacements or the slopes. which we got finally. The slope values will be according to the coordinates. The first coordinate is the point B, so first we will get theta B. The second coordinate was the point C, so here we will get theta C. In this analysis, we have calculated both of the unknowns. Now, let us make the slope deflection equations and find the final moments. First, let us make the slope deflection equations in the span AB. We have already calculated the fixed end moments. Let us apply them. Length of AB is 4 meter. Let us apply that. In the point A, there is a fixed support. In the fixed support, there will be no slope. So, theta A will be 0. Let us cut theta A and make it 0 in both of the equations. After applying the value of theta B, we are getting MAB and MBA. Now, let us make the slope deflection equation in the span BC. No need to make the equation for MCB because we have already calculated MCB. Only make the equation for MBC. In this equation, let us apply the fixed end moment. Length of BC is 5 meter. Let us apply that. After applying the values of theta B and theta C, we are getting MBC, which is equal to minus 51 kilonewton meter. In this analysis, we have calculated all of the moments. In this analysis, we have calculated all of the moments. Now, we are going to find the vertical reactions. First, let us take the span AB and calculate the vertical reactions. In the span AB, there are two moments, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. By taking moment about B, we can calculate RA. By applying the rule sigma V is equal to 0, we can calculate RB1. Now, let us take the span BC and the overhanging span CD and calculate the vertical reactions. When we take these two spans together, no need to consider MCB and MCD. They will get eliminated because one is acting in the clockwise direction and one is acting in the anti-clockwise direction. 30 minus 30, it will be 0. In this case, we have to consider only MBC, which is acting in the anti-clockwise direction. By taking moment about C, I am calculating RB2. Then applying the rule sigma V is equal to 0, I am calculating RC. Now let us add RB1 and RB2 so that we will get RB. Now we are going to make the shear force diagram. Before drawing the diagram, let us calculate the shear force values. I am moving towards right hand side. Upwards will be positive and downwards will be negative. Using the values, we can draw the shear force diagram. Now, using the loads, we can draw the free movement diagram. Using the end moments, we can draw the end moment diagram. Then we have to combine the end moment diagram and the free moment diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.